Okay, we are ready to start. Just a quick recap on where we are. As I said, this is the last lecture by me, and then the next teachers will start with a different calendar. Please make sure that you get an update of the scheduling, and we are teaching in continuity, so they will pick up what I have done. And in the list of the links in my web page, here, there is one additional link besides. Here you see that there is also design, the last link, design of climate change adaptation actions, and probably we will not use it. What it is not used during the lecture, it's not a subject for the exam. So just, I will leave it there anyway for your information. But if we don't use it, and if my colleagues don't use it, because it may be that my colleagues decide to teach on that, it's no subject for the exam, okay? I'm sure that we will finish today with climate and energy. I'm not sure I left time to start the last lecture. In any case, you use the rule that what is taught in the room during the lectures may be the subject for some questions at the exam. What is not discussed here, you can forget it, okay? Of course, the link is there for your personal information if you want to go through it. Climate and energy, just a brief recap, because a lot of information is given to you in this lecture, a lot of data. So what is the purpose here? First of all, energy generation plays a key role in determining climate change. As we have seen, 72% of the human emissions are due to energy production, which may be used by transportation, may be used by electric cars, may be used by other for other purposes, but it is, of course, playing a key role, and therefore, also for climate change mitigation and adaptation, energy plays a key role. So it is extremely important to know, on the one hand, what is the purpose for generating energy, why we need energy, what are the forms of energy that we can exploit, primary energy versus other forms, secondary energy, and it's extremely important that you can distinguish between them. It's extremely important that you remember this classification. You will find for sure questions in the exam like, is coal a primary energy source or not? And is crude oil a primary energy source or not? And etc. And then there are a lot of information on how energy is produced, who produces it in terms of countries, and what are the sources, again, the sources for energy production. This is important in order to understand what are the options that we have available, and in order, therefore, to understand strategies for optimizing the use and generation of energy, okay? And we also focused on the difference between energy and electricity. It's a different story. Electricity is a form of energy, but energy is more general. We know that most of our uses are also related to electricity. Of course, when we talk about generation of electricity, the sources are different. So, for instance, hydropower accounts for only 2% of the global energy generation, 2-3%, but accounts for about 19% of electricity generation. Again, knowing this data, it's important for understanding what are the options. I'm providing this kind of discussion reflection because, of course, so when you get a lot of data, you may get also confused, like, okay, what is the purpose of giving me all of this information? The purpose is stated in the lecture notes, but it is indeed, the purpose is indeed that you need knowledge on what are the forms of energy that we can use, how energy can be generated, and how we use it. Okay, because I am also providing information on what are the uses for the energy that we generate. Okay, so we did most of it, and I'm browsing very quickly. One key message that comes from this information, which is extremely important for you, is that fossil fuels still account for about 80% of human energy generation. Okay, first. Second, renewable are still a limited amount of it, but it is increasing. Renewable are now accounting for about 20% of energy generation. It is increasing. And renewable has another key message, a problem. The problem is reliability, continuity, flexibility. It is energy source, the renewable energy, that is not very flexible. And it's important because you have to take into account that electricity cannot be stored or can be stored only in small quantities. And therefore we cannot say, okay, we use solar panels to generate electricity when the sun is strong and we store it. It's not possible. We can store only on a limited quantity, like for instance, in batteries for cars, but it is very limited, as you know. And also energy, in general, it's difficult to store. There are some options for storing energy, and I mentioned water. Water is hydropower, is a good energy. We can store hydropower in reservoirs, and we can indeed also use energy that we cannot store in order to bring water upstream, to pump water upstream, so storing energy in the form of hydropower. Okay, hydroelectricity cannot be stored, but hydropower, yes, can be stored. There is a say for making clear that hydroelectricity cannot be stored, but hydropower can store. And the say is that whenever you turn on a light in your room, there is somewhere, if the electricity is provided by hydropower. So I state it again. When you go in your room and you turn on the light, okay, like today I turned on the projector, and the electricity to turn on the projector is given by hydropower, as it is likely here. It means that when you turn on the light, there is an hydro turbine that is accelerating, because there is hydropower stored in the reservoir, and we cannot store hydroelectricity. So it means that you turn on your light and there is an hydro turbine that is accelerating because electricity is not stored. But indeed, the key message that renewable in general are not flexible is another key message of this lecture. Okay. Total world energy consumption, renewable energy, progress of renewable energy capacity, production of energy by country. It's important in order to understand what strategies are possible, what kind of international trading is necessary. Okay. And then we talked about the potential for renewables. We talked about renewables extensively, the potential, so wind energy generation by region, wind power density potential, and global horizontal irradiation, which means solar energy potential. And there are links, so if you want to better understand, if you want to get additional information, these data are open, are public. If you see them on the screen in my lecture notes, everything can be reached by you, okay? And solar panels, we discussed about the problems, the environmental impact, because when we talk about renewable energy, we also sometimes use the term clean energy. Actually, clean is not a good term. I think renewable is a good term, but renewable energy has an environmental impact. If you think of hydropower, for instance, a lot of people wouldn't agree that it's clean because the environmental impact is very significant. Indeed, when we try to build new reservoirs, the reservation by people are extremely vocal. You know, this is one of the reasons why today we are in a bit slowing down in hydropower generation, hydroelectricity generation. We are slowing down because the most interesting opportunities have been already used, but we are also slowing down because of the reservations of the citizens, of the public. And therefore, we talked about the environmental impact, and we also talked about the cost, the price, because sometimes renewable are more costly than fossil fuels. More costly means that the citizens find into the tariff they find an increased price. And this is something that usually we don't consider. Sometimes we attribute to politics the responsibility for not taking action. Actually, sometimes the opposition to taking action is by citizens who are concerned by the environmental impact or are concerned by the increase of the tariff, because, of course, people like to reduce the emission, but if you ask them to pay, there is the problem that some of them cannot pay, and therefore there is disparity, inequity, and there is also the problem that even those who can pay, of course, they don't agree because of the cost, and an important consideration is regarding the time scale, because you see, the price of the photovoltaic panels is declining. What does this mean? It means that in the future, probably, it will decline even more. And therefore, it may be advisable to wait a little bit, because if we realize solar farms later on, first, the duration becomes longer in the future. And second, the cost probably will be less than today's cost. So the time scale is also very important. And keep in mind that this in general applies when we talk about decarbonization, or we talk about specific actions to decarbonization, like electric cars. What is not convenient today may become much more convenient in a few years from now, like in 10 years from now. If you look at the progress of this decline in the price of photovoltaic panels, is a progress from 1975 through 2021. And you see that indeed it's a decline that took place in a relatively short term. And today, progress is moving forward even more quickly. And therefore, the time scale is also important. But what I would like to talk about today is nuclear energy. And nuclear energy, and then, as I mentioned in the last lecture, I want to talk about the water-food energy nexus. But first, nuclear energy, because this is a really strategic subject. Let me open a PowerPoint that is dedicated to nuclear energy. And it's available in here, PowerPoint presentation on nuclear energy, and it's here. Okay, good. So first, I mentioned to you that I'm not an expert in energy engineering, and then I'm not an expert on nuclear energy. And therefore, just take into account that if you are interested in energy, and if you're interested in particular in nuclear energy, there are other courses that you may take at the University of Bologna, but whatever, which provide more detailed information. Mine is just an introduction. And I'm focusing on issues that probably most of you already know. But still, I think that we really need a discussion on it. Why? Because you know that this is an hot topic. I mean, nuclear energy is relatively recent because the process of producing energy through nuclear fission or fusion, and we will see what is the difference. But fission is splitting an atom. Fusion is creating a new element by putting together two different atoms. And therefore they are opposite, you know. And so the discovery that by breaking atoms or putting atoms together, we may obtain an exothermic reaction. So we may obtain a reaction that delivers energy. Is relatively recent. The discoveries were done around in the 1930s, 1940s. And probably I have a slide dedicated to that, not really. So let me just go back to the web page and give you some more information on that. About the discovery of this possibility, nuclear energy, just 1 second. Okay, so the first discovery was related to nuclear fission and dates back to 1938. And when we humanity created the first person-made, human-made nuclear reactor, the Chicago Pile 1 in 1942, okay, with an experiment led by Enrico Fermi. And later on, this led to the development, the discovery of the atomic bomb, as you may know. And the first was, I think, was used in 1945 at Hiroshima. I think. I'm not sure it was really the first one, because, of course, other tests probably were done earlier. And the atomic bomb used this idea, the idea that by breaking an atom, we can, breaking the nucleus of an atom, we can deliver a lot of energy. And then we started using the nuclear reaction in order to produce energy, and in particular electricity, in a, let's say, in a positive way. And then we started around 1960 with a peak, with a rapid increase. So the first energy centrals, the first plants, nuclear plants for electricity production were realized, I think, in 1960. Yeah, the date is not here, but it is around the 1960s. And then they increased a lot in number in the 1970 up to the 1980s, increased a lot, especially in the Western world at the beginning, and then also in the Eastern world. On the other hand, you have to take into account that these first plants used the nuclear fission because, as we will see, is logistically more convenient. And we are not yet ready to build nuclear plants based on nuclear fusion, because nuclear fusion is more difficult to manage. We will see why. So nuclear fission, however, has an inconvenience. The inconvenience is that when you break the nucleus of an atom, then some protons are released, which may hit the other atoms by generating a chain of reaction, a chain of ruptures of nucleus. And also some radioactive isotopes are generated. This means that it is extremely important to control the chain of reactions. First, because, of course, you need to control the energy production. Therefore, also we need to stop the nuclear plant. We cannot accept it we cannot govern the production of energy, because you understand that we cannot accept an excess of energy generation. But the problem is made even more complicated because given that radioactive isotopes are generated, these radioactive isotopes need to be controlled because radioactivity is dangerous for the human health. And radioactivity naturally decays, but the decay is very slow. And therefore there is, first of all, a problem of disposal of the wastes, of the scores of the generated isotopes, radioactive. They have to be disposed in a safe place with safe conditions for a duration of time that is extremely long, because these isotopes take a long time to decay, and therefore radioactivity is active for a long time. And for this very reason, we cannot accept the risk, or it is extremely risky if the reactor breaks. If you have a proliferation of reaction chains, they can break the reactor, and because the reactor is a controlled chamber, so if the reactor gets broken, of course, it is a big problem for the amount of energy that we get spread outside, which means heat, basically. And it is a problem because of the radioactivity, which is spread outside. So at the beginning, we thought we devised, of course, ways of controlling these reactions through the introduction of bars, of neutral bars, which they are put into the fuel. The fuel is essentially uranium, or uranium-like material. So we put these bars, which are neutral, which means that they cannot be broken, and their material of which they are constituted is not subjected to breaks of the nucleus, so they are not subjected to nuclear reaction, and therefore we put these bars into the reactor, into the fuel, into the uranium, in order to control the reaction chain. But of course, it is a very delicate process. And at the beginning, we were not fully aware of the amount of energy, and we were not fully aware of the danger. And the technology was not granting the ideal level of safety. So what happened? It happened that in 1969, in 1979, and in 1986, we had two accidents. So the first one was occurred in 1979, and occurred at the 3 Mile Island reactor in the United States. In 1986 was Chernobyl, especially Chernobyl, which originated a spread of radioactivity over the whole of Europe, had a very significant echo, and the result was that people got much concerned. First of all, you have to take into account that in any case, in our minds, the nuclear energy is related to Hiroshima, is related to the atomic bomb, is related to the nuclear weapons. And therefore, there is already an association which is explicit with nuclear energy, with something that people really don't like much, something very dangerous, something very powerful. And then the occurrence of this accident sorted out the results that people got very against, very vocal in opposing to building new nuclear plants. And you may know that in Italy, for instance, we had a referendum where people said, no, we don't want nuclear plants in Italy. And therefore, the few that were very active in Italy were shut down. And overall, in the Western world, the production of nuclear energy reached a cap. So from the 1980s in the Western world, there was not a significant progress, a very small progress in a very small trend in the production of nuclear energy. Conversely, in the Eastern world, they continued, and they continue to build new nuclear plants. So this is a brief history, and today, I would say that from 1980 and 1980s, 1990s, up to 2020, 2015, 2020, in the Western world, there was a hiatus and a general consideration by people that nuclear energy was over, like something that we have to avoid. After the onset of global warming, actually, people realized what are the implications and realized through the contribution of science that global warming is probably due to human emissions, and realized that human emissions are mainly related to energy production, and that because 80% of our current energy production, and in 2015 it was even more than that, it was close to 85, was obtained by burning fossil fuels and therefore generating significant CO2 emissions. So people started to wonder what are the possible solutions, and renewable, yes, but more and more we became aware of the limitations. The limitation is what I mentioned, namely reliability, flexibility. And therefore, it became clear that we needed a more comprehensive reassessment of what are the options for energy production. And then nuclear energy came back in the consideration of first politicians and now the general public. Because meanwhile, the technology is improved. So now we are in the condition of ensuring more safety. It is like if you think about artificial reservoirs, the first that we built, some of them collapsed. But then we understood from these incidents, and also we progressed in the technology. Now, artificial reservoirs are not considered a big risk. And the same is occurring for nuclear energy. We are improving the technology. And so it's clear that today the risk would be lower. Still, there is the problem of waste disposal, but the risk would be a bit lower. And there is another issue, another important consideration to make about fusion, nuclear fusion, because nuclear fusion is really progressing well, and it is definitely safer, much safer, and doesn't involve radioactivity, is much safer than a nuclear fission. And therefore, there is a question that is emerging. Nuclear fusion, we are not yet ready, but there are predictions that by 2035, so in 10 years from now, we will be able to build the first nuclear fusion plant. And therefore, it means that this is really a convenient option. It is becoming a convenient option. There is also, and we are not discussing about it, the solution of the hydrogen, of the use of the hydrogen as a fuel for cars and some cars moving with hydrogen has been already produced, but they are not yet ready to be regularly produced because the technology is still in its infancy, but it is another possible option. So now the relevant question is, should we accelerate in decarbonization? Is it reasonable that we put targets on decarbonization on 2030 or 2050 when we know that in few years from now we may be able to promote, to use more convenient technologies for energy production? So is it convenient that now we spend a lot of money for building solar farms which are not flexible? Nuclear energy is flexible, by the way. So they are not flexible, and they have a huge environmental impact. Solar farms, like wind farms, shouldn't be better that we wait 10 years. We decelerate a little bit our timeline to transition, to energy transition. in order to profit of solutions that would allow to mitigate the environmental impact and would allow to mitigate the cost, which is a social cost. It's not a cost that is paid by the politician, it's paid by us, by people. And therefore, this is the consideration. And it's a debate that is really taking off. Taking off, where it's also a political debate, and it's taking off, and therefore we need also, from a scientific point of view, to get informed about it, to get information, to really see, really being able to participate to this debate and to look beyond what is the pure evaluation of the politicians. Attending these debates is extremely important. Attending these debates by people is extremely important. But in order to attend a debate, you need information, especially if you are a technician, you are a professional who has something to say in terms of solutions, in terms of practicality of a solution, in terms of impact of a solution. It is necessary to be informed. And this is why I decided to take back some consideration on nuclear energy in my lectures. And let me go back to the PowerPoint. Okay. Keep in mind, just to give you an idea, that up to 1999, 2000, there were in many universities in Europe courses, master degree programs on nuclear energy. And now they disappear. They disappear because we didn't get any more students. Now we substituted them with energy engineering, for instance, which is also talking about nuclear energy. But the impact, the emotional impact that was generated by these two accidents, Chernobyl and previous, was such that nuclear energy got really a stop. And only now we are starting to reconsidering it. Keep in mind that it's still a hot topic. Okay? Still a hot topic. So how does it work? A nuclear power plant is a thermal power station. So with nuclear energy, with the nuclear fission and fusion, we generate heat. We generate heat that is converted into electricity with production by heating up water or some other fluid, and therefore generating electricity through steam, water vapor. So the heat is used to generate steam, as you see here, who drives a steam turbine. This is the traditional solution. Then there are other solutions that are being developed, that were developed later, but the traditional solution is to drive a steam turbine connected to a generator. And so how many power plants do we have? In September 2023, the International Atomic Energy Agency reported that there were 410 nuclear power reactors in operation in 32 countries around the world, and 57 nuclear power reactors under construction, especially in the Eastern world. So you see that overall, they are not many. We are talking about, if you put the numbers together, 467 power plants, nuclear power plants, not many, and only 32 countries. So, and this means that there are countries that may have many, but other countries, of course, don't have any. There is to say that, in order to minimize the risk with nuclear fission, it's also important that they are displaced in areas that are poorly inhabited. And for obvious reasons, because you minimize the exposure. After an accident, you minimize the exposure. Because it takes some time in order radioactivity to spread, and while spreading, some radioactivity decays. And therefore, if you put them in a very desert area, it's much better, of course. And you can't avoid that radioactivity spreads. As I said, Chernobyl spread over all Europe. But on the other hand, it's it's if they are in desert areas, it's much better. You have more time to react. And just useless consideration, the negative implications, the negative impact of radioactivity on the human health is proof. There is no discussion on that. Okay? Unfortunately, the people who worked to stop the reactor, the Chernobyl reactor, most of them died within a few years. Okay, so this is how a reactor works. It is a traditional, it is a scheme, a very simple scheme of a traditional nuclear power plant. So you have a vessel, which is a kind of school around which contains the reactor. Okay, it is a chamber, a closed chamber, where you get into it the fuel core elements, and in red, number 2. And then you have the control rod element, what I called bars before. They are put inside the fuel in order to control the reaction. Okay? And then there are pumps that help to circulate the water, because into this scheme of nuclear reactor, you have water inside it, and the water is pumped. Look at the cold water is pumped. Look at the blue pipes through a circulation network, and then basically the water gets heated by the nuclear reaction and goes to the number 8, which is a high pressure turbine. Okay, and there is a high pressure turbine and a low pressure turbine. Why high and low pressure? Because we want to be very efficient in generation of electricity. And the turbines must be sized depending on their nominal capacity in order to have a good efficiency. And therefore, if you split them into 2 turbines, you can use the most of efficiency, the high pressure, and the most of efficiency, the low pressure. And then these turbines generate the yellow line, an electric generator, which produces the electricity. Okay, number 12 is the steam condenser. The steam condenser helps to recover the water, to condense the remaining part of the vapor, and to put again water in circulation. The condenser is refrigerated by circulation of cold water, which helps the condensation. And the cold water is taken by, of course, an external water source. And we try to keep the water that goes into the reactor confined into the pump. So the water that comes from the external into the plant, the water that comes from outside doesn't get in touch with the water that went into the reactor because of the radioactivity. So the water that goes into the reactor is radioactive. So you understand why all of this is put into this gray block. You understand the importance of keeping radioactivity confined into the plant. So how is the water warmed up? When you break with nuclear fission the atom of uranium, the atom goes split into 2 radioactive isotopes, and with this split, there are protons that are freed, that are made free, and these protons, after the split, travel at a very high velocity, so they have a lot of kinetic energy. With this lot of kinetic energy, they can trigger new reactions, and due to the effect of friction against water, they warm water up. So it is kinetic energy that is produced with the nuclear fission, which is transformed into heat with friction, and then later on in electricity through the generation of water vapor. And that's it, basically. An important consideration. The amount of energy that is generated is massive. Even with small quantities of uranium, the amount of energy that we can generate is like something like, with the same quantity of uranium and coal, the amount of energy generated by nuclear fission is like 10,000 more, 10,000 times more. So there is no comparison. It's 4 orders of magnitude with the same amount of material. What does this mean? It means that even if nuclear energy is not in principle renewable, because uranium is not unlimited, however, compared to the fossil fuels, it's renewable. And it's renewable. It's in practice, we can consider it renewable, especially if we consider that with the progress of technology, we have other materials that can be used besides uranium. Still, when we talk about nuclear fission, there is always the generation of radioactivity. So the main problem here is not the fact that the fuel is limited or it's available only in some countries. Of course, if we rely on nuclear energy a lot, then the countries who owns the uranium becomes in a favorable position, like with the use of natural gas. The countries who have the natural gas, they get in a favorable position, or the countries that can exploit fossil fuels are in a favorable position. But on the other hand, I mean, the uranium is quite widespread, and it's very powerful in electricity generation. And once again, this is flexible. This mechanism is flexible in energy production. Of course, provided that we can safely control the chain of reactions. This is another animated figure. The scheme is similar. This is nicer because, as you see, it's animated, but you see, it's similar. So here you can see also the pressurizer, which was not so evident before. And here there is a little bit of a difference, because there is here you don't see the water getting into the generator, but you see that the radioactive material is kept separated in this scheme here. And indeed, this is another possibility that with the progress of technology we devised. So this is in principle it is in principle safer, but it is more or less the same scheme. This is an image of a nuclear power plant. What you see there, what looks like smoke, is water vapor. It's not smoke. Okay. Actually, it is quite clean because, okay, there is the problem of the radioactive scores, but on the other hand, there is negligible CO2 emissions. CO2 generation is negligible. It is related maybe to the maintenance operations, but it is really negligible. And also in terms of environmental impact, if there are no accidents. And they are also in terms of visual. Okay, of course, here you see something that looks not very nice, but on the other hand, if you consider a dam, or if you consider a solar farm, if you consider wind turbines, are much more impacting. So really here, the big problem is radioactivity. Okay, so is it so dangerous? this graph says that no, it's not so dangerous, actually, because this is, of course, it's an hypothetical number. And of course, it's hypothetical because how can you relate, how can you compute the death due to the use for energy production of coal? Okay? But this is an hypothetical number of deaths from energy production. And so this is numbers that were derived, would have resulted if the world's energy production was met through a single source. And so you see that brown coal is the most dangerous. The coal is the most dangerous. And then there is the oil, the biomass, the gas, and the nuclear. Of course, you know, these numbers you have to take it as an indication, but you see that indeed what we see is that the nuclear plants are not so dangerous, actually. It is like a paradigm. We think that taking an airplane is risky. On the other hand, it has been demonstrated that it's less risky than traveling with individual cars. So if everybody traveled by plane, the number of deaths compared to the situation where everybody travels with individual cars, it's much less dangerous. And for instance, and also traveling by plane is also less risky than traveling by train because, but it doesn't look like that. And so also for the nuclear, of course, this is a graph that is hypothetical. And when you see something of hypothetical, of course, you always have to look for several sources of information. But still, I believe it is indeed reliable, what is shown here. But on the other hand, there are strong reservations. And we are talking about nuclear fission here. Fusion, once again, it's an option, but it's still not used. We are not yet ready to use nuclear fusion. So when you see this information, nuclear is nuclear fission. Okay, so controversy. I think we already discussed it. And there are only, sorry for this slide, which is very long, so you don't need to read it. And but there are also, because you don't need to read it, because several of the considerations that are reported here are already gone, and we'll discuss them. But on the other hand, there are a few additional considerations that we have to do. So basically, the opponents of nuclear power, they bring up the reservation that it is indeed an enormously complex machine, a reactor. So the reactor, what they say is we had few deaths up to now because of few reactors. But they estimate that these graphs report of the risk is an underestimate. These numbers underestimate the risk because if I look at the complexity of a nuclear reactor, indeed, it's much more complex with respect to hydropower, with respect to the use of fossil fuels. And these risks cannot be really evaluated in their entire amount. So it is true that we had only a couple of accidents, but if we look at a couple of accidents over 400 of nuclear plants, 450, the number is 1 over 200, which is quite relevant. So this proves that the complexity is underestimated, okay? And so, I mean, the debate is still very active, okay? So in terms of slides, I stop it here. But there is some more that I would like to say, which is not in the slides, which is about nuclear fusion. Okay. So nuclear fusion is, what is nuclear fusion? Nuclear fusion is a nuclear reaction that occurs, for instance, in the sun and in other stars. And with the production, we know of an enormous quantity of energy. And it's obtained when two nuclei of light elements, such as deuterium and tritium, for instance, at high temperature and pressure, we need a very high temperature and a very high pressure, fuse together to form a nuclei of heavier elements. So there are two elements that join and form an heavier element, such as helium, with emissions of large quantities of energy. And I'm sorry for the noise, but I'm not sure I am successful if I try to. And given that we have only 10 minutes before the break, I think it's better if we try to stay patient a little bit. They don't realize actually that the noise is coming in, but anyway. And two light elements that we put together to form a heavy element, and a lot of energy is produced. A lot of energy is exothermic, so direct heat is produced. And but the two nucleus can fuse only if they are brought to a very short distance, which means a lot of pressure and high temperature. In the sun, the pressure is obtained with the enormous gravity force. So the gravity force over the sun, of course, for the mass of the sun is very strong. And the result is that these elements are put very close to each other. And because of the gravity force, in our case, we need to put pressure, like we make when we want to increase the atmospheric pressure, we use a barometric chamber. And the need for this very high pressure is what is still limiting the production of nuclear energy from fusion. And because we need very high temperature, about 100 millions of degrees, and this is the temperature that is in the sun, even higher than that. And we need also a very high pressure. And so this is the technology that we still need. We need to develop. We need to develop good technologies that can be applied serially to produce high temperature and high pressure in a small chamber. But then, at the end of the story, the helium that is produced is not dangerous. So we have much less problems in waste disposal, and we don't have the problem of radioactivity. So indeed, nuclear energy is, nuclear fusion is something that is taking off in the consideration also of politicians. And you see that the European roadmap towards fusion electricity envisages the construction of the first reactor that feeds electricity into the grid in the second half of the century. Mi chiedo scusa, sto facendo un sonno, devo spostare, devo scusate voi. Okay. Indeed, this is a roadmap that is coherent with what I said, that we believe that the technology will be ready by 2035. And that's it, I would say. Okay. And now we are ready to make our conclusion about the importance of the overall water, food, energy nexus. Importance with respect to climate change. So we talked about the relevant role of energy production in climate change mitigation and adaptation. And when we talk about the relevant role of energy production, we talked about hydropower, so the significant role of water into it. But water is also essential for food production. And indeed, when we talk about artificial reservoirs, we have in engineering the problem of deciding what are the priorities. So should we use the water for food production or should we use the water for energy generation? In some cases, they may be compatible, but actually it's not easy. It's not easy because first, you may remember, because we discussed it some time ago, that indeed water consumption for food production is the major, is 70% of the human use for fresh water, which means high volumes. And also this water is stored in the reservoirs, but cannot be stored downstream unless you have a second reservoir. This means that once that you release the water for producing energy, in the same way as we cannot store electricity, we cannot store anymore the water for irrigation. It cannot be stored in the soil. If I need to irrigate in June, because irrigation now in Italy, but let's say in the middle latitude countries is needed from April to August, with the peaks in June and July. In Italy, it is the peak of irrigation is June and July. And we start irrigation in April and we end up irrigation in August. But during this period, we don't have much need of electricity. We need more electricity during the winter for obvious reasons, because the day is shorter. Of course, I mean, for the industrial production, there is no seasonality or little seasonality. But for the civil use of electricity, there is a lot of seasonality. And there is not coincidence of phases. So it is a relevant question whether I should give the priority to electricity generation or to food production. And there is a third priority for artificial reservoirs, which is becoming more and more important, is flood mitigation, flood risk mitigation. Because the reservoirs, they change the river regime, and they change the water flow, and they change also the peak flow. Because if the reservoir has some spare volume, during a flood, the reservoir can retain water, thus reducing the risk out downstream. If conversely the reservoir has not spare volume, it may happen that once it gets flooded, they need, in order to get overtopping, in order to avoid overtopping, they need to release water from the bottom discharge. And they may need to release, they may end up releasing more water than the volume that is entering, therefore increasing the river flow downstream. And this clarifies that they can play a key role, but in order to play this key role in a positive direction, we need spare volume, which means that we cannot take the reservoir full. We have to reserve part of the volume. Indeed, this is prescribed by law. There are some reservoirs where the law in force says that you cannot use the whole volume for irrigation or for hydropower production during the flood season. So if the flood season is coincident with the irrigation season, usually not that much, or with the seasonality of electricity production, if they are in a phasing in a way that is not convenient, then of course the nexus becomes even more complicated. So this is why recently the scientific literature has proposed this concept of water food energy nexus, which is quite simple to understand. I mean, in conceptually, it's very simple because I could summarize it in 5 minutes. On the other hand, to explain the implications and to quantify the implications is not easy because you need to inspect the connections So what is the damage that is caused by a flood? What is the damage that is caused by a lack of irrigation water? And what is the damage that is caused by a lack of electricity in the electricity network that is served by a given reservoir? You have to quantify all of these links. And when you make the quantification, it means that you elaborate a mathematical model, has to rely on some assumptions, like what is going to be in the next 5 years the cost of electricity, what is going to be the cost of some foods. So how will behave the market of energy, the market of food, and how can what other solutions we have available for mitigating the risk of flood. And when you discuss, when you quantify these links, these implications, of course there are assumptions, there is subjectivity, and therefore the discussion with people becomes extremely complicated, because you may say, for instance, let's forget about flood mitigation. Flood mitigation can be obtained by raising the levees downstream. And people may say, no, sorry, I don't trust the levees, because if you raise a levee, then the risk becomes even larger, because it means that my house is staying behind a wall of water that is 15 meters high. So, I mean, if you think of a levee, usually the max height that is reached by a levee along the Po River is 15 meters. It means that if you are living there behind the levee on the land side, during a flood, you have a wall of water that is like 5 layers of a building, like a building with 5 levels, just in front of you. And if the levee fails, can you imagine? So people may not like it. And therefore, inspecting this nexus by reducing as much as possible uncertainty, by reducing as much as possible the assumptions, and by developing a good capability of explaining to people what is the implication, becomes extremely important. So this is the reason why you see a sketch here and not mathematical equations, because we need to interact with people. We need to discuss with them, and we need to build public acceptance of a solution, which is, as I discussed already earlier, not easy, because the public in general is reluctant to change. And therefore, if you propose to build a reservoir, they say no. If you propose to build, to raise a levee, they say no. And therefore, communication becomes extremely important. And again, this is why these nexus very often are presented through sketches, which, by the way, I believe are still too complicated. When you put in a sketch too many arrows going in a direction and the opposite direction, then communication suffers. We need to explain these linkages in a better way than what you can see. It is still too complicated. And I think this is a problem of the scientific community, because scientists like complexity. Of course, they don't want to make things very easy for many reasons. But first of all, because it's their task to study complexity. And therefore, they are happy when they can show that they succeeded to interpret complexity. But on the other hand, when it goes to communication, and this is why sometimes I say communication, it's a task for professional communicators, not for scientists. Because a scientist, when it goes to communication, I think it's not very effective. And it is not easy also to remember this sketch, this diagram. I think it should be simpler. Anyway, this is really important, because it clarifies what is the complexity of the whole discourse that we made on energy production. And I would say that we can make the break now, and then I will dedicate the last hour to saying something to design of climate change adaptation, actions for climate change adaptation. Questions? Okay, let's make the break now, and we will meet again at 3 plus couple of minutes. Okay. So, let me see. Okay, so this is our last topic, which is climate change adaptation. And in particular, what I would like to do is a very brief focus on the design, the procedures that we design for, we should design for, we should follow, the procedure that we should follow to elaborate design projects for climate change adaptation. This is a relevant open problem because it's clear that we need to take action against to cope with climate change. But on the one hand, it's not very clear what type of actions we should adopt in view also of the limited amount of resources, in view of the high costs that these actions require. On the other hand, it's an open question how we can evaluate the forcings, how we can develop design projects, which is very important for engineering, of course, design projects for these actions. I say design projects because these actions involve, in many cases, the development, the building of infrastructures like dams, artificial reservoir, which we just discussed. And of course, in order to elaborate these design projects, we need to know the loads, the forcings, and in particular, from the point of view of engineering, the loads. And the loads for these infrastructures are typically originated by climate. It's climate forcing that generates the loads, like peak river flow, like volume of water flow, for which we have to design these infrastructures. And even when we talk about air conditioning, for instance, we need to know what is the future temperature that these devices will need to mitigate. And therefore, knowledge of the future climate is essential. On the other hand, we discussed several times that there is a lot of uncertainty in the estimation of the future climate. And therefore, it's an open question how to estimate these future loads in the presence of climate change, and therefore how to elaborate these design projects. So we have two questions: design projects on the other end, and on the one end, what kind of actions? We already discussed the two main categories of actions that we may take, which are climate change mitigation on the one end, the climate change adaptation on the other end. And mitigation means, as we said, that we try to mitigate climate change. We try to reduce climate change. We try to stabilize climate. And there are several options, but the most the popular is decarbonization. Climate change adaptation means that we adapt to a changing climate. So we accept that climate is changing and we adapt to it. There are several pros and cons for both of them, but the most important consideration to make is the cost because of the limitation of the resources. When we talk about climate change adaptation, this is a typical engineering problem. It's a topical engineering problem. It's an engineering problem because climate change adaptation very often requires design projects for infrastructures. Of course, there are some adaptation measures, and in particular, the nature-based solutions, which may require not so relevant effort from the point of view of engineering. But at the end of the story, in any way, we have to deal with the quantitative estimation of loads and the capability of the solutions to cope with the loads. And this is a typical, again, engineering problem. So there are some solutions for climate change adaptation that are really hard engineering, other solutions that are soft engineering, but it is anyway a typical and topical engineering problem. And it's an engineering problem because we have to evaluate the environmental impact, and then we may be required to evaluate alternative solutions, and we have to evaluate the time scale of over which these infrastructures, these solutions operate. Keep in mind that they have very different time scales, mitigation and adaptation. Mitigation takes a longer time to get positive results, to get a benefit. Adaptation is more effective in the short time. On the other hand, adaptation may have some limitation in the long term because, of course, if climate keeps changing, we have also to consider that the adaptation solution will need to be updated with new strategies or by adapting the strategies themselves to the climate that we will experience in the future. And keep in mind that adaptation requires an engagement with stakeholders. And when I mentioned communication, when I mentioned the water, food, energy nexus, I already highlighted the fact that adaptation requires a dialogue with stakeholders. When we talk about decision making to cope with climate change, we can identify two categories of approaches. A classical approach, which is the top-down strategy. So I already mentioned it. We start with a prediction of future climate, and then this prediction of future climate identifies the loads, and then basing on the loads, we develop the design project. Typically, in the top-down approach, the term top-down also means that the decision is taken by the authorities down to the stakeholders. It's the authority that, maybe by using a scientific consultancy, produces an estimate of the future climate. It's the authority that then, maybe with scientific consultants, elaborates the load and decides the solution. In the past 15 years, got increasing popularity the so-called bottom-up approach. The bottom-up approach reverses the workflow. It relies on an assessment of the existing problems, vulnerabilities, of the existing risk. For instance, because a flood occurred or a heat wave occurred, and then there is a clear indication of a vulnerability, of a risk. This risk is discussed with the stakeholders, and competing solutions are taken into consideration for resolving what we have quantitatively assessed after an event, for instance. And then the discussion moves forward to the durability of these solutions. What if climate will continue to change? Is the solution still effective? Can be adapted? Is a no-regret solution? Or there are other solutions that give get more support in these terms. There are other solutions that are more flexible, more successful if climate keeps changing. And then we can use in this stage climate scenarios to get an idea. So, okay, climate will change, but how much? And we use the climate scenario. What is the big advantage? The big advantage, we can identify two reasons, two motivations for identifying, for seeing a big advantage. The first thing is that we focus on the current problems. So we have a problem, we solve it. And this removes part of the uncertainty, because if you instead need a climate scenario produced by a mathematical model to identify the problem, it means that you have some uncertainty. Basically, a current problem is something that we really see because something occurred. And the second reason for benefit advantage of the bottom-up approach is the involvement of people. Because, of course, given that we know that today is the resistance of the public that is indeed very often a reason for unsuccess, then by involving people at the beginning of the consultation, we set the basis for a more productive action. Of course, the bottom-up approach has some limitations because involving people means involving additional resources for communication, and what happens when you get into different interpretation, contrasting requirements from people, then it's a problem. And we need decision-making to come decision-making into play. And the whole process, which is basically the process that we are following now, gets slowed down. It becomes very slow, very lengthy, because you need to talk to people and then to try to reach convergence. It's a bit of a problem. I mean, the top-down decision where there is an authority which takes the responsibility of saying, we do this, it's for sure more efficient in terms of timing. Of course, for being successful, the top-down approach needs to rely on a good support, good information, good decision, wise decisions. And then it's, in a way, in a democratic system is more difficult to apply. But for sure, there is a key step that is shared by the two categories of approaches, which is risk estimation. We need a risk estimation, even if, no matter if it is based on a climate scenario or on an event that already occurred, we need risk estimation. So what is the procedure that we should follow for estimating the risk? Keep in mind that the risk against a climate forcing is determined by several drivers, several concurring situations. Because if you have a climate change, but in a desert area, it doesn't produce any risk. We define risk as a damage that is occurring to people, to the society, or a damage that is occurring, yes, to the environment, but usually if the environment is undisturbed, like in a desert area, it has the capability to recover autonomously. in the long term, maybe, but this is not a concern. So it's not just climate change. There must be also some vulnerability of the social setting, some value in the social setting to defend. So what is the procedure that is followed? And this is what I want to anticipate in this half an hour, because I think it is extremely interesting. So I'm skipping all the considerations that we can make in a way, the consideration, because there are several slides dedicated to the workflow of the bottom-up approach, which is not very relevant to us at this stage. I just would like to focus in this half an hour on the risk estimation. And the risk is estimated through the relationship that you see on the top of this graph. Forget about the graph now. I just projected this slide because it puts in bold the risk equation, what we call the risk equation. R is risk on the left-hand side. P on the right-hand side is hazard. This depends on climate. And it is indicated with P because P stands for probability. So hazard can be quantified through probability. What is the probability of getting a flood? What is the probability of getting an heat wave? What is the probability of getting an earthquake if you want to refer to earthquake risk? And this is strictly related to the environment. The earthquake is related to geodesy, not to geodesy, sorry, to geophysics. And for the other risks that I mentioned, flood, drought, or heat wave, it's related to climate. So based on climate, you estimate the probability, the hazard, the probability of the considered event, and therefore the hazard. The hazard doesn't mean risk in itself, because if you have a high probability of flooding in a desert area, you don't produce any damage to the societal context. So it's not only us. Okay? I don't care if I have a huge probability of an earthquake in a desert zone, completely desert. I don't care of it. It's nature, it's fine. Also flooding, it's nature. Environment has the capability to react because it's nature. But I need an estimate for this probability because, of course, if I don't have the hazard, if there is no possibility that I get an earthquake, there is no risk. Okay? So I said that when we deal with climate change, probability is estimated based on climate, and you have two options. Top-down approach, you produce a climate scenario. Bottom-up approach, you first refer to historical data, to historical climate. An event occurred, okay, what was the probability for that event in the historical climate? And then you may make a check with climate scenarios later. Okay? So P is probability. What is vulnerability? Vulnerability, one thing. Probability is defined in the theory of probability. Let's say that in general, probability of an event occurring is a number that is comprised in the range extremes included 0, 1. This is explained in my slide, in my lecture notes, not here, but it's a number dimensionless between 0 and 1. So if I say probability of an earthquake is 0, we all know what it means. If I say probability of an earthquake is 1, this is a bit less comprehensive, less understandable for us, because in our reasoning, we could say it's meaningless. I cannot say that an earthquake will occur for sure. On the other hand, I may say, that we can never say that an earthquake is impossible for sure. But anyway, you understand that this number, if it gets close to 1, means that the event, the hazard becomes higher and the event more likely. And so between 0 and 1, you have this quantification, which can be done based on the historical climate data or climate scenario. Dimensionless. Vulnerability is the second term V. What is vulnerability? You may have a community that even if the event occurs is completely safe, like earthquakes. You have a city with buildings that are earthquake proofed, for sure. So you say vulnerability is zero. On the other hand, or like you get a flood, but the river has levees that are absolutely safe, no matter that, no doubt, they will resist. So the flood will stay into the riverbed. So people will not get water. Vulnerability zero. On the other hand, you may say, if a flood occurs, unfortunately, I have no protection. So people will get water. You understand that this vulnerability depends on the magnitude of the event. So I may be safe with respect to a flood up to a certain limit, but then above that limit, I'm not safe anymore. And vulnerability is dimensionless, again, quantified with the numbers between 0 and 1. Vulnerability 0 means I am dead safe, and vulnerability 1 means that I am completely vulnerable. If the event occurs, I am affected. You understand? Vulnerability 0 means that you don't care about the hazard, and the risk is 0. Exposure, the last term in the right-hand side. What is exposure? Exposure is the value of the goods that are affected by the event. So let's suppose that you have a community that is exposed to floods. The community is completely vulnerable, but there is no value. What does it mean, no value? Not only economic value. There is no economic value, but there is also no value in everything that can be affected by floods. For instance, because people cannot die. Like urban flooding, people usually in a urban flood, they don't get killed. So one may say, okay, there are no houses that can be damaged, there are no people that can die, so exposure is 0. And usually it is expressed in terms of economic value, especially in the insurance sector. This equation is widely used by the insurance sector to determine the fees that people have to pay to get insured. So exposure, as I said, usually it's an economic value. It's unconfined. It is only positive. The only limitation is that it is a positive value. You cannot have an economic value that is less than 0. It is from 0 to infinity. You understand that if exposure is 0, you have no risk because you don't get any damage because there is no value to protect. Okay? And then you take a multiplication of P, V, and E, and you estimate the risk. And the risk is expressed in economic terms because P and V are dimensionless. And, or let's say, risk is expressed as a value. And P and V are dimensionless. If E is expressed in economic units, then you have also the risk in economic units. And then you can elaborate also conceptual meaning of risk, which is average damage that you can get in a certain time step, depending on how probability is defined. But we don't want to go into the details. Just it's important that we know that there are these 3 determinants which concur in forming the risk. It is interesting to look at the progress of these multipliers depending on the intensity of the event. And here we have a graph that shows in the horizontal axis the intensity of the event. What do I mean with intensity? For instance, the scale of an earthquake, the grade, okay, like Richter 7, Richter 5, Richter. This is the intensity. Of course, for increasing Richter, it's increasing the intensity. In terms of flooding, maybe the water depth that you get into the city, water depth of 10 centimeters or water depth of 2 meters. And you understand that these are completely different situations. If you get 2 centimeters of water, you say, who cares? And if you get 2 meters, you are concerned by people who may die because 2 meters. Or another thing for the flood could be a combination of water depth and water velocity, because actually in the floods, it's not only water depth the problem, it's also water velocity. Because even such amount of water, if it runs very fast, can bring a car away or people away. Okay, so depending on the intensity of the event, the question is how the intensity of the event depends on probability. So it can be proved that a very unlikely event is more intensive. I mean, if you get like an earthquake that is very unlikely, it is a strong one. Of course, a minor earthquake is more likely. So basically, the intensity is another way to express probability. And here you can expect for increasing intensity a decreasing probability. And this is why I wanted here to show the intensity instead of the probability, because the intensity, has the advantage for graphical representation that increasing intensity is obtained by moving in the direction of increasing numbers. Probability is the opposite. Probability, the low probability events are those more concerning. So I prefer to write here the intensity of the event, but you can consider that we can prove, we don't do that, we can prove that there is a direct relationship between the intensity of the event and its frequency, which means probability. Okay, so here I have, let's say, probability. Okay. Now, I just said that the vulnerability depends on the probability of the hazard, on the intensity of the event, but not only vulnerability. And vulnerability, you can think of something that up to a certain intensity, your vulnerability is 0. But then with an increasing intensity, you get to vulnerability maybe 1. And with a progress that really depends on the considered case, on the considered situation. So here is just an hypothesis, but you may have vulnerability starting increasing from 0 or whatever. This is just an hypothetical situation. Not only vulnerability is increasing, also exposure, because if you get 2 centimeters of water, you get no damage. If you get 2 meters of water, it means that the full level of an house is interested, and then you have a damage, and also the risk for the life of people. So also exposure, we can assume a similar pattern. 0 up to a certain threshold, and then it increases, okay? Now, what happens to risk? Risk is the product of the 3, but with probability, not intensity. And probability goes down for increasing intensity. So it may happen that you have a situation, an intensity of the event that determines the max risk. Because if you go further in the intensity, the probability becomes so low that you are not concerned anymore, because it's the risk, it goes really down. Like, for instance, if you were reassured that a certain event occurs with a frequency of 1 in 2,000 years, you would say, why should I get protected against something that happens so rarely? It means that, getting protected with something like that implies a cost in terms of actions that it's not worth the effort. It's not worth doing. And of course, it depends on the type of damage that you get. For instance, the laws in Italy prescribe that urban drainage is sized with respect to any events that have a high probability of occurring. Why? because even if it occurs, we are not concerned. It's a low amount of water. Instead, when we talk about dams, the laws suggest that they are designed against an event that is very unlikely. It means it's very extreme. Why they do that? Because a dam break means a lot of people dying, beyond down 2000. So they don't want to take this, even if it is very low. But usually in a cost-benefit analysis, you look for a compromise between the cost of the action and the damage that you get. And that is interesting that in this case, you may set to size your actions against the event that gives the maximum risk, which is a maximum expected damage. And so you take the max of the expected damage. This is basically the risk approach. And then, of course, you have to introduce models for evaluating the probability. Because no matter the kind of data that you use, like climate scenario or historical data, which means present climate, you need a probability model. So the flood that occurred in the Romagna region 2 years ago, what is the probability? People spent a lot of time in trying to understand what was the probability. They use also the word return period in engineering. In engineering, they say return period is a synonym of probability, is a synonym of intensity of the event. They spent a lot of time, a lot of consultancy activities to try to estimate the return period. Why? Because if we need to get protected, if we want to design actions in order to get protected, we need an estimate of the hazard, which means the return periods, and you need a model. You need a model for estimating vulnerability. What is, in mathematical terms, the degree of vulnerability that corresponds to a given LEV? There are a lot of assumptions that you need to make, and a model for exposure, which is typically a socioeconomic model. And this is what the insurance companies are expert in doing. In evaluating the socioeconomic impact, they are very expert. They take an approach that may seem like something cynical. They give a price also to the human life, and they are very good. But they often ask for a consultancy, in the estimation of probability, because they are not expert about climate change, and therefore they want to know the effect of climate change on the probabilities. And so you need to put together these mathematical models. The procedure becomes complex, but not really so tough. We have a lot of literature for everything. And the thing that may be tricky is the information that is required, information collection. Because indeed, in order to set up these models, you need information. You need information on climate, and we discussed it. You need information also on the river network if it is a flood, because if you want to estimate what is the benefit given by a levee, of course you have to know how the levee was built and how the levee is maintained, if there is surveillance, if there are mammals that dig their homes into the levee, and if there are actions to prevent the action of mammals, of burrowing animals. And for instance, part of the damages of the Romagna region, for sure, have been originated by burrowing animals that dig their homes into the levees. And so getting this data, it's not easy. And also getting, of course, the data on the socioeconomic asset is not easy. So this is basically what I wanted to introduce. And here, of course, there is an explanation, but I already discussed it. And now I think it's time for me to make some final considerations. Just let me know. Okay, good. I think I very quickly I said everything. And about this lecture, you may find some questions in the exam, but they are essentially related to bottom-up and top-down approaches, and the risk equation. Where is it? Here. This equation here. So what I discussed again, okay? So let me make some concluding remarks related to what I discussed with you. And let me go back to the web pages. Again, this is the list of the links, and I just would like to very quickly go through them with you and highlight what could be a question for the exam in order to help you to give some support in getting prepared, okay? So first of all, once again, what was discussed in the room and only what was discussed in the lecture room is a subject for questions at exams. So what you see in the links of my webpage is not necessarily only what has been discussed in the room. And even if you see in the lecture notes something that was not discussed in the room will not be used for your exam, okay? And pay particular attention, given that it's a quiz with closed answers. I think you are more expert than me in understanding what can be the subject of a closed answer question. It cannot be a descriptive topic, a topic that was essentially discussed through a narrative, because a closed answer session question needs to be the question has to be very quantitative, very clearly stated, and also the solutions, the answers cannot be very long sentences in which you have to choose what sentence is correct. The alternatives very often are numbers or terms like what of these is a form of primary energy, and then you see something like crude oil or other 2 or 3, 4 alternatives that are clearly not primary energies, and you have to understand that crude oil is the source of primary energy by keeping into account that there is only one correct answer and there is no penalty. So basically, if you are in doubt, just try, okay? And so if we go through these lectures, what could be the subject for a closed answer session? Okay, difficult, the great acceleration. So, I mean, a question cannot be, what is the great acceleration? Because it may be very difficult to distinguish between competing alternatives. So it's not very quantitative, okay? But on the other hand, you may find a question on the definition of weather and climate, like what is the correct definition of climate among the 3 solutions below, and you find one is the correct one, and the other one are clearly distinguishable, because you understand that in order to convince you that you made a mistake, I need to make the alternative answers very well distinguished after a careful reading. So for instance, definition of weather is weather refers to the day-to-day state of the atmosphere, okay? Or climate describes the statistics, I think it is statistics, describes the weather of a place averaged over a period of time. So one alternative is the correct answer. A second alternative maybe describes the weather of a place, and I don't put averaged over a period of time. This is to give you an example. So they have to be clearly distinguishable after a careful reading, okay? Other thing, there are numbers, where there are numbers, global temperature is raised about 1.3. This is for sure may be a question in the quiz. How much has increased the global temperature? Alternatives, 0.1, more than between 1 and 1.5, more than 10, or between 5 and 10. Okay, this is very easy. I mean, very easy to state and very easy to recognize the answer. And sea level rise, same thing. Global CO2 emissions, orders of magnitude. Remember, nobody wants you to know that has increased from about 5 to about 35. But the alternative may be from 5 to 35, from 50 to 350, from 5,000 to 35 millions. Okay. So try to keep these numbers well clear in mind. Okay, and this is the first. Second, the climate change problem. Here there is not much, okay, not much. And if you go through it, you understand that, okay, you may find a definition, question, what is solar irradiance, but unlikely, too easy, okay? And, or you may find some question about future emissions, but future emissions meaning that what is business as usual scenario, and then you find some alternatives. But this is a lecture where, in general, I don't see many possibilities for asking questions. The Earth system, yeah, here there is something, because you may find something like the definition of what is the hydrosphere, or something related to, let me see, these numbers. No, don't focus on too many numbers, because I focus in my questions on the numbers, that few numbers that can be well remembered. And yeah, nonlinearity maybe for sure there are some questions related to what is linearity, how to identify linearity, nonlinearity, what is a tipping point. Yes, this may happen. So there is something, but deterministic stochastic models, I wouldn't say, it's unlikely. What I'm saying, please don't take it for granted. It's indications, okay? And that's it. And then climate models, yeah, there might be something. Look for what is quantitative, and then something easy to remember, and then you may find, even if I don't think it is really climate change and water cycle, we skipped it, remember. Okay, we didn't use this link. And for this last link, we only used the risk equation. The risk equation, you will find it in the questions. Okay, this is also the reason why I took the opportunity of doing it. And there are some questions on the history of Earth climate, and you may find it. And the questions may be something like, what is the behavior of temperature in the Holocene, which is the current epoch? And it is substantially stable. You may remember that we said the Holocene was characterized, was a favorable period for humans because temperature was substantially stable. Okay, or other questions may be like about the fluctuation of temperature in the past, the very macroscopic features. Okay, so the medieval warm period may be that you find a question: what was climate behavior in the medieval warm period, and then the answer is easy to be identified. And then there is climate and energy. Here there are a lot of possibilities, because you have here conversion, energy conversion, and like a question may be something like combustion. What kind of energy transformation operates from chemical to thermal? Okay, and this table here, please be careful, primary and secondary energy. And some macroscopic feature, like what is the main source of human emissions of CO2, energy production. Okay, and you will find alternatives like energy, industry, agriculture, waste, whatever. Okay, and what are the limitations of renewable energy? And So just look at these numbers. Nuclear energy, there are no questions because you don't see any really quantitative information here. So that's it, basically. And of course, as I already mentioned to you, I am available if you have any doubt may also be that we see each other again because maybe that I substitute my colleagues. But in any case, if you have any doubt, just contact me by email and I can answer by email, or we can have an appointment over Teams. Okay, so questions?